Bismillah ar-Rahman ar-Rahim. Now my son, we are going to practice some examples related to the concepts of magnetic field due to arced wire. So my wire has a shape of an arc, okay, as you can see it here, in this figure here. And the figure, a closed wire, loop wire, see this is a closed loop wire, it's closed wire, carrying a current of 4.4 ampere. The current has a direction, okay, see, you can see it. Is here it is clockwise, here to the right, so I can write it here to the right like this. Here counterclockwise, and here to the right also, okay? The current I, these two wires. So so he wants the magnetic field. He wants the magnetic field in the at point P due to these wires, okay? He wants and these arcs, the two arcs, they have a radius R1, 4 meters, and the radius R2 here, radius R2 from this point is 8 meters, and he wants the magnetic field in the center here. These two wires, these two arced wires, they have the same center, by the way, huh? And he wants the magnetic field in the center here, P. As you know, if you go back to the concepts, when you have an arc like this, any arced wire, okay, any arced wire like this, okay, the magnetic field in the center of the wire, in the center of, if you continue this as a circle, at this point in the center R, the magnetic field is mu0 I theta, the angle, okay, the sustained angle here, theta, okay, over 4 pi r. That's from Biot-Savart law. This is given to you, it was given to you in the concepts, when we were discussing the concepts. That's the magnetic field. And this angle here actually is in radian, okay? So, I is the current in the wire, the current, R is the radius of this arc, and this point P is the center of, if you complete this complete circle, this is the center of the circle, okay? That's the center, and that's the center P also here, which is if you complete a circle here, that's the center of the circle. Any other points, it's not, the formula is not valid. It's valid only at this point here, and theta is in radian. If you give an angle of 90 degrees, this is pi over 2. If it is 180 degrees, that's pi radian, and so on, okay? Now, he wants the magnetic field due to those wires. Remember also, I did this in the concepts by doing ds cross r. If you have a wire like this, with the current I, at this point P, the magnetic field is 0. That's the extension of the wire, okay? Because of, there was in the Biot-Savart law, ds cross r, this the cross product, ds cross r, and that's in this case, ds and parallel to r, so ds cross r will give you 0, and this magnetic field is 0 at the extension of the wire. So you have a wire, current wire, at the extension here at this point, the magnetic field is 0. Very important, okay? So let's, so here we have 4 wires. We have this wire, I'm going to call it number 1, this one number 2, this one number 3, and this one number 4. It is clear at this point, the current, the magnetic field to wire number 3 and wire number 1, they are in, the point is in the extension of these 2 wires, so the magnetic field will be 0 for those two wires, okay? So wire, so I'm going to call B1, I'm going to say B1 equal B3 equal to 0. B1 equal B3 equal to 0. The magnetic field due to these 2 wires, because of this idea here, okay? Now, let's go to B2, okay? And then B4, okay? B2 will be mu0 I over 4 pi R2, okay, the radius, times the angle phi, or theta, sorry, the angle theta, and the angle theta here is pi, okay? So this will be 4 pi into power minus 7, that's the mu0, times the current is 0.4 ampere, times pi, the angle, divided by 4 pi, times the radius R2, which is 8 meters, okay? 8. So this 4 pi cancel here, and if you do the calculation correctly, you should get for B2 0.157 into power minus 7 Tesla. That's the magnetic field B2. Now, my son, you have to tell me what is the direction of this magnetic field. The direction of this magnetic field. So, since the current is in this direction here, okay, like this, you use your fingers, okay? The thumb will be the current from this side due to this wire 2, B2. From this side it's in, and from this side, from the bottom it's out. So this is outside, okay? So this is outside the page. When I say outside, I mean the page, okay? So that's the magnitude of the magnetic field, and that's its direction, okay? Let's go to B4 now, okay? B4. B4 is due to this wire here. Smaller radius, okay? Is mu0 I. What is the angle here? Sustained by this arc here is pi, okay? Is pi over 4 pi r r1. And mu0 is actually, okay, so let's write the numbers here. So 4 pi into power minus 7 times the current, same current, 0.4, times pi over 4 pi times 4 meters, okay? 4. So it will be half of this value here, okay? It will be twice this value, sorry, twice this value. 0.3, it will be 0.314, okay? 0.314 into power minus 7 Tesla. That's the magnetic field and its direction, right-hand rule. Now the current has a reverse direction here. It is counterclockwise, the current here is clockwise. So you put your fingers with the thumb with the current, and the magnetic field will be inside from this side, okay? So it will be inside, okay? Inside the page. Inside the page. That's the direction of the magnetic field, okay? Here it is outside, and this is its magnitude here. As you can see, so the magnetic fields, they are not in the same direction. One of them is outside, has a bigger value, smaller value, sorry, and one is inside, it has a bigger magnitude, okay? So what will be B net then? B at point P, the net magnetic field will be the outside. The outside will be, so it will be 0.157 into power minus 7 minus the minus because of it is inside, okay? 0.314 into power minus 7, and this will give you minus 0.157 into power minus 7 Tesla. The minus sign is the indication that it is inside, okay? Yeah, it is inside, okay? So magnetic field is inside. That's the net magnetic field at point P, magnitude here. That's the magnitude of the magnetic field. Magnitude, and that's the direction here is given by the minus sign here, okay? That's how you would solve a problem which is related to an arced wire. And this is a complicated little bit because it has four segments. 2 of them are straight wires, and fortunately the point P is here, and we use this idea here. When the point is at the extension of the wire, the magnetic field will be 0. And this is what we found here. B1 and B3 are 0. Now, B2, you use this formula here from Biot-Savart law, and you get the magnitude and direction. B4, you use the same formula, you get magnitude and direction, and then you have to, the outside is positive, the inside is negative, okay, inside is negative, and then you get a minus sign because of the direction here, and the magnitude of the magnetic field is this. What is the magnetic field at the center? Point P. So this is its magnitude, and this is its direction. In direction, you can write it down here. It is inside, okay? It is inside. Thank you. Okay, this is another example related to magnetic field due to an arc wire. This example here shows, this is a problem which shows this arced wire. This is a loop. Actually, it's a loop. You can see it. But the 2 arced wire are in different planes. The first one is in the XY plane, and the second one is the XZ plane. They are perpendicular to each other. I hope you can visualize this figure here, okay? Now, he wants the magnetic field at point P, which is in the center of this semicircle. By the way, we call this semicircle, it's half a circle, and this is a semicircle. Both of them, they have the same center, and this point is in the center. So I can use the Biot-Savart law for the magnetic field in the center of an arced wire, mu0 I theta over 4 pi r, okay, where r is the radius. I can use this formula here, okay? Now, I have 4 wires, as we did in the previous example. This wire here has a current in this direction, and the current here is in this direction. And the current here is to the right. Of course, these 2 straight wires, their magnetic field here is 0, as we explained previously. Yeah? This point is in the extension of these 2 wires, left and right, the straight wires. Magnetic field is 0. I'm not going to discuss that. I'm going to discuss the magnetic field due to these 2 arcs. And the angle here is pi, and the angle here is pi. So theta is pi in both cases. But this time, be careful, the 2 vectors B are not in the same plane. They are in different planes. Actually, they will be perpendicular to each other. Let's see now, okay? Let's take wire number 1. I'm going to call B1, okay? B1 is mu 0 I pi over 4 pi R1. I'm going to call it R1. The radius R1. This is the radius R1. And that's the radius R2 for the small wire, okay? For the small arc. All right? So this is 4 pi to the power minus 7. Current is 0.4 ampere. It's given to you here. Sorry, 0.5 ampere. The current is 0.5 ampere. The radius for that wire is 10 centimeter. Pi here, I'm going to write the pi. And 4 pi here, the radius is 0.1. Okay, 4 pi will cancel. And you calculate this. B1 is 15.7 to the power minus 7. 15.7 to the power minus 7 Tesla. That's the magnitude. Now, if I want to write it as a vector, B1, it will be 15.7 to the power minus 7. Now, I have to write its direction. So, the current is in this direction, okay? So, magnetic field at this point is pointing in this direction here, B1. B1 is pointing outside, which means parallel to the z-axis. It is parallel to the z-axis and in the positive z. Yeah? So I have to write here K like this. And then Tesla, the units, okay? That's the direction of the magnetic field. Plus sign, plus, along the positive z, okay? Now let's go to B2 now. The magnetic field due to the other wire, 4 pi to the power minus 7 times 0.5 times pi, the same current, everything the same, except the radius, okay? Now the radius is 4 centimeters, which is 0.04. So if you do calculate correctly, you should get 39.3 and to the power minus 7 Tesla. That's the magnetic field. Now its direction now B2, okay? B2 is 39.3 and to the power minus 7. Let's write which unit vector we have to use. This is the unit vector along the z-axis. Now the current is in this direction, so the magnetic field will be pointing upward, okay? Upward, you see here the current pointing upward, perpendicular to this plane here, okay? The plane, the xz plane, so it's along the y-axis. So I have to write here J, unit vector Tesla. That's the magnetic field B2, okay? So if you want now, I have a magnetic field B1 along the z-axis, and I have a magnetic field B2 along the y-axis, so and they are perpendicular to each other. So if I want the net magnetic field, the magnitude of the magnetic field at point P, which means he wants the net magnetic field, B net. So B net will be 15. So let me write the J component first. Will be 39.3 and to the power minus 7 J plus 15.7. You write down correctly here, 15.7 and to the power minus 7 K. That's the vector B net, okay? If you want the magnitude of B net, the magnitude, it is simply square root of 39.3 to the power minus 7 squared, because these two vectors are perpendicular, plus 15.7 to the power minus 7 squared, and you take the square root. We are using Pythagoras here to find the magnitude of the magnetic field, which will be 42.3 to the power minus 7, 42.3 and to the power minus 7 Tesla. That's the net magnetic field in magnitude. If you want it as a vector, this is what it is. Thank you.